So everything we've done until now has always focused on a single straight pipe, and it's just one pipe system. So we have tools that allow us to solve problems where we have a pipe, where we have a pump, and we have just one line of, just one where all of these, all the sections technically would have to be the same diameter. So they could have components in them, but throughout the entire piping system, if you have the same diameter throughout each component, we have all the tools to be able to calculate head losses in terms of piping systems. We don't have the tools actually to analyze what happens when it comes to different styles of pipes, or if you have a situation like this. This has a different type of problem. This is a different type of problem than what we've been doing because there's a separation right here in terms of the flow rates. So that means the velocities dropping. You don't have this constant velocity. You even have to figure out what flow rate's going this way and what flow rate's going that way based on all of these things. So that's what we're going to head in. That's what this whole process is about, is how do we extend these methods knowing just parts about the individual parts of the pipes. So this is a single pipe section. But we want to talk about this sort of multi-pipe system, right? So how do I talk about losses when it comes to these multiple pipes flowing all at the same time? And that's what we're going to talk about right now. And it comes down to these sort of three fundamental multi-pipe problems, and that is we have pipes in series. Right, pipes in series would be ones that go from here to here. So let's say another. So this is D1, D2, and a D3. This would be in series. The other problem are pipes in parallel. Right, and that is the situation when you have flow rate in, say through a pipe, and then it breaks up into sort of like a array like that, where this is like pipe 1, pipe 2, pipe 3. You have the flow rate that's going in, and there's a certain law with that. And then the third one is pipes and junctions. So this is a situation where you have, let's say, a pipe, something like that. I ran out of space, so I'm just going to erase this. So the junction problem is one where you have like reservoirs that flow down here. There's another one. There's nothing here. Something like that. So we have this junction point right here. That's called we'll call that point the J, or the junction point. So those are the three main types of problems that we can solve based on the tools that we've developed so far. Right, and everything will still come down to these three laws. So for series, the law we have is that we know in each section the flow rates are constant. Right, the flow rate, for each section pipe, the mass flow rate in this one to this one and this one all have to be equal. So that's the main equation we apply to solve that type of a problem. Okay. Now for parallel pipes, what we do sort of a node law, where if I have three pipes running like this, I know this Q total. This one has Q1, Q2, and then Q3, what we apply there is this law that all three flow rates have to sum up to this. And then for the junction, it's really just, for the junction, we just have a special rule that's, which is a specific case of the parallel rule. If you have a bunch of, right, going to some type of junction point J. So here's Q rate 1, Q rate 2, and let's say this is actually Q rate 3. We just then say, for the junction law, it's that 0 is the sum of all of these. And that's nothing more than what you did in circuits, right? Where you're really just saying at a junction point, you can't generate fluid mass. So whatever comes in has to go out. So that's this idea of these arrows, right? Whatever 2 went in, this has to be going out. So, right, one way you can just really think about this is you're saying that Q3 has to, right, in terms of if you had negative signs on these things, that it has to be equal to Q2, where this has to be a negative, right? They have to sum up, regardless of the algebraic signs, they have to sum up to 0. So that's just I think it's the Kirchhoff's law for circuits. And that's really the techniques we use is we just mimic what we did in electrical circuits.